Okay, in this screencast, I'm going to formally show how the Foucault pendulum works and try to find a solution of the equation and see how the Coriolis effect is in fact responsible for the precession of the plane in which the Foucault pendulum oscillates. So it turns out that all we need to solve this problem is this equation there, which is on the bottom of the screen. And the way we obtain this equation is actually pretty straightforward. We realize that Newton's law is only valid in a fixed frame. In other words, in an inertial frame, by definition, an inertial frame. And usually when we are on Earth, we actually use a rotating frame. Of course, we do not realize it, but the place where we stand still on the surface of the Earth is actually a rotating frame because the Earth is rotating around its axis. We are going to ignore all the other effects like revolution or of the Earth around the Sun or any other effect. So really we are going to focus on the effect of the rotation of the Earth around the axis. The axis of rotation is shown on this picture with omega being the angular velocity. So we are going to use the system of coordinates that's shown there in the black lines with Ex, Ey, Ez, and that system of coordinates moves with the rotation. In other words, that even though that point rotates, the point O rotates, we are going to sit as an observer placed at point O. Okay? So in other words, we are in a non-inertial frame. And we know, in principle, Newton's law cannot be valid in that rotating frame, but it's possible to make it work if we correct the forces. So the way it's done, it's actually pretty much shown on this equation on this screen that shows that we need to use an effective force. So if we use that effective force, then we can use Newton's law, so F equal m times the acceleration, but we obviously need a correction. So in this equation, S represents all the surface forces. We are not going to worry about that for the Foucault pendulum. There is no additional forces other than the gravity. So mg is actually not just the gravity, it's the gravity corrected for the centrifugal force. So otherwise we would have written mg naught, but there is a correction that we have seen in a different screencast. However, what's the important term that we are going to focus on this is the third term. That term is related to what's called the Coriolis force. And we are going to show that the Coriolis force, which only shows for a rotating system and for an object moving in the rotating frame, so rotating, moving means Vr is non-zero, Vr meaning the velocity in the rotating frame. So only an object that's in a rotating frame and it's actually moving in the rotating frame will have a Coriolis force. And this is what we are going to do now. And it's called the Foucault pendulum. The Foucault pendulum is the idea that, that the plane in which the pendulum is actually oscillating is not constant. Actually, the plane moves, precess, moves about, so rotates. This is something that we love to see, and many physicists actually got motivated to do physics by going to museum where a Foucault pendulum is very often shown with a very, very long pendulum. And we see that it's actually moving around. I will show a picture of that at the end of this short screencast. So we will only worry about small oscillations, just like we usually do for a pendulum, so that we keep linear equations. Okay, so first of all, this is another picture that I already showed you in the previous slide. What we will need is the different vectors. So in this slide, I'm going to introduce all the vectors we need from the previous equation. So the first vector we want is omega. And we picked the axis Ex, Ey, and Ez so that Ey is perpendicular to omega, so there is no omega y. And the two components Ex and Ez, omega x and omega z along Ex and Ez are given by minus omega cos lambda and omega sine lambda. So this is something that you can see clearly from the geometry. So I invite you to maybe pause the screencast at this point to convince yourself that these coordinates are just coming from from the triangle that we have there with angle lambda. Actually, lambda is a well-known number. It's actually the latitude. That's what we use to find the point on Earth, how far away from the equator we are. So we use the latitude lambda. Okay, now we know also that we have a pendulum. So the pendulum is actually has forces on it, which is going to be the tension due to the rope itself, and then the gravitational force. So there will be, if you look at the picture on the left-hand side, you see that we have the tension has component along x, y, and z. Typically, when we solve this without worrying about Coriolis force, of course, T and mg are the same, and this is the reason why actually the pendulum doesn't move up and down along the rope. But we also have a component along x and y, which is related to the position of the pendulum x and y. That's again shown on the picture. This is another opportunity to maybe pause the screencast and convince yourself that those numbers are correct. So I just like to say Tz is almost equal to T. Of course, it's a little bit smaller than T. It's, of course, if it was equal to T, the norm would not be correct, but it's almost equal to T because we use a length of the pendulum extremely long. So that means that we have the projection is essentially the same as if it were infinitely long. Okay, now the other thing that we are going to need is the gravitational force. Again, it's the gravity that's corrected for the centrifugal force that we have already discussed. And so we suppose that we do not have a component along x and y, and we have one along z. And when we suppose, we actually do not suppose. This is a consequence of our choice of axis, z being normal to the point O that is the origin of the rotating frame. Then we also look at the velocity, because we are going to need the velocity. Remember that the Coriolis force will be omega cross Vr. And the velocity will have component x dot, y dot, and we will suppose that the object does not move much along z. It's actually not exactly true, of course, because as you know, as the pendulum moves, the z component change a little bit. But if we have small oscillation and the length of the pendulum is long, the z dot is essentially 0. So we end up having to solve this equation for the acceleration. That's come directly from the previous slide. In fact, in the previous slide, I said that S was equal to 0, but in fact, in this case, really S is the tension that we need to keep the bob at the end of the pendulum at the position L from the fixed point of the pendulum. So we have everything we need, really. We have G, T, omega, and Vr. So the usual way to calculate the cross product omega cross Vr, and remember omega is a vector that's along the axis of rotation, it's shown on the picture. Well, we actually use a determinant. It's pretty straightforward. We obtain this equation here. We simply introduce this determinant with the second line being omega and the third line being Vr. And we obtain this component pretty straightforwardly. And then we see that this is essentially the Coriolis force related to the Coriolis force acting on the pendulum here. And so when we now put everything together, the acceleration is due to the tension, is due to the gravitation, and it's also due to the Coriolis force, and we obtain this acceleration. You see, of course, there is no g showing up because we said that we chose the axis so that there is no component of the gravity along x and y. So these are Newton's law, which, as we know, should not be applicable in a non-inertial frame. However, because we added the non-inertial forces, particularly the centrifugal force and also the Coriolis force, then we end up with those equations to be valid. Okay, this is very good, and now we just have to solve these equations. So the equation we have to solve are these. I just repeat them from the previous slide. And we are going to start by noticing that the tension T is almost equal to the gravitational force. Indeed, if we have a small displacement and very long arm of the pendulum, the tension is pretty much the same as mg. Okay, we are going to suppose to have very tiny displacement here. This makes sense. So that's going to help us to make things a little bit simpler. And we are going to define a number alpha square, which we are fine to use as a positive number because t and mass and length are all positive numbers. And these are going to be equal pretty much to g over L since t over m is g. Okay, there's nothing very complicated. And once again, we know that from a couple of slides ago, we saw that the component along z of the axis of rotation, so omega z, is equal to omega sine theta, alpha sine lambda, where lambda is the latitude, and omega is the scalar that represents the angular velocity. So with all this said and done, we get the new set of equations that we have there, which are second-order differential equation, and we see directly that these are coupled equations of motions where the x and y are mixed in the two lines. So there are different ways to solve this. You can solve this numerically. That's pretty simple, but actually we can solve it analytically as well. And it turns out that one trick to use is to multiply the second equation by I, so square root of -1, and then we add the left-hand side and the right-hand side, and we end up with this equation. So you see directly this equation. The real part is the first equation, and the imaginary part is the second equation. And of course, we do this because it looks pretty nice. Why? Because now, if we introduce a new complex variable q, which is x plus iy, if we do that, then the equation becomes much simpler, actually much more compact, at least, not simpler necessarily, but more compact. And this is really the equation we need to solve. So this is an interesting equation that we realize to be, that we understand to be a typical equation that we've seen in different areas of physics. I'd just like to tell you one thing that's quite obvious, is that if there is no rotation, so if omega z is equal to 0, we end up with the usual equation, a very simple equation to solve. And it's actually, in that case, there is no precession, of course. We also notice that there is a term in this differential equation that depends on the velocity. And as we know in physics, when we have a term in such an equation that depends on the velocity, usually corresponds to a damping term. But I like to be very careful here. It's a damping term, but the damping is purely imaginary. So it's not really a damping per se. So a damping would mean a decrease in amplitude, but here it's an imaginary one. So instead of a decrease in amplitude, it's going to correspond to a rotation, as we are going to see. So it's basically a dephasing. So anyways, I'm going to just give you an outline of the proof of how to solve this, and then I'll show you an example. So this is the equation we need to solve, and we see that the solution to this can be written in this form. This is an exact form that we have. We actually know, it turns out that alpha that I described before as related to the tension and the gravitational pull is actually numerically a much larger number than omega z. Remember, omega z is of the order of 2 pi per day, right? So it's a much smaller number than alpha. And that means that the solution to this equation is essentially obtained by replacing omega z square plus alpha square by alpha square, okay? And then we do that, things simplify tremendously, and we obtain this equation, which is, of course, an equation for x and y. And then we see directly that the component of x and y are oscillating with frequency omega z, right? The second term of this equation is actually the equation you would get without an omega z. And so the rotation of the fact that x and y are rotating, so are moving, is related to the first term. And this first term is actually showing that the plane in which the pendulum is oscillating moves at a frequency omega z. So it's actually this Coriolis, this effect, this Foucault pendulum is actually a way, and it's a historical way, in fact, that shows that the Earth is actually rotating. If the Earth were not rotating, we would not have the first term, and therefore no precession. So it's actually interesting in physics that when you see something that there is a precession of something, like a pendulum, that means there is some physics that's not obvious, right? I can remind you the precession of the perihelion of Mercury is also a proof of the existence of general relativity. So you see this is actually interesting to see the parallel here. So we see that the plane oscillates oscillation rotates with frequency omega z. Now, let's try to remember what omega z was. Omega z is a component of omega, of the vector omega of rotation, so the rotation axis, is the projection. It's actually multiplied by sine lambda, where lambda is the latitude. And so you see the latitude on the equator, for example, lambda is equal to 0. Therefore, there is omega z is equal to 0. So there is no Coriolis effect on the equator. So if you were doing the Foucault pendulum experiment on the equator, you will actually not see any precession. That's actually shown there on this picture that I found on the internet. On the other hand, the effect will be the strongest at the pole, the North Pole or the South Pole, right? Why is that so? Well, because in the North Pole, lambda is equal to pi over 2, and in that case, the sine of pi over 2 is 1. So this is where omega z is the maximum. So at that place is where you have the largest effect. Actually, many museums, as I said at the beginning of the screencast, have a Foucault pendulum installed, and in fact, most of those museums are around 40 degrees of latitude. And then you see, indeed, that you have the pendulum does not stay in the plane but moves. And this typical picture that you've seen here is an example of one that's in Spain. The way that's usually done in museum is that you see that the pendulum oscillates but moves slightly, rotates slightly, and you have those little these balls here or whatever, these specks that are actually dropping more and more. And how long does it take to go around? Well, it takes time for the full rotation at frequency omega z. So if you were at the pole, it would take 1 day, a full day, because omega z equal to omega at the pole. So this is actually the Foucault pendulum. This is historically very important because, as I said, it actually demonstrated that the Earth is actually rotating, and it's a purely Coriolis effect. So it's a very interesting thing to do, and it's not very complicated to describe this mathematically, as we've just done in a little bit less than 8 minutes, so long as you understand well that the reason why we could solve this is because we're using an effective force that is built such a way that we can apply a Newton's-like equation, even though the frame in which we use it is non-inertial. Thank you very much for your attention.